Okay, let's unpack this. I want you to think about the most fundamental assumptions we make about reality.
Hmm. The things you just don't even question.
Exactly. The speed of light, gravity, and maybe the biggest one, the one we rely on every single second, is time itself.
The constancy of it.
Yeah, the idea that a minute is 60 seconds, period. It doesn't matter where you are, it's just 60 seconds. It's our constant.
It's the bedrock of modern life, isn't it? Our entire civilization is built on atomic clocks and this stable rhythm, this
Yeah.
60-second container.
Right. We just assume that if we run an experiment for 1 minute here on Earth, that exact amount of time has passed everywhere else.
Mm.
But what if that foundational assumption is, well, just flawed? Not because of some weird black hole physics, but because of something as simple as how fast a planet spins.
And that's what's so fascinating about the source material we're looking at today. It challenges that whole idea just by comparing us to Mars.
We are diving deep into this idea of temporal constancy. We're asking why a basic everyday unit like the minute is. Well, it's actually variable.
It really forces you to realize how many of our definitions are just
Hmm.
Earth-centric. They're not universal truth.
So our mission in this deep dive is to get to the core of this. The shocking fact that on Mars, a minute is measurably longer than a minute here.
And this isn't theory. This is concrete.
Exactly. For anyone listening who loves a surprising, tangible fact, this is a big aha moment.
And that initial shock is key,
Mhm.
We're conditioned to think of time as being totally independent of location.
Yeah.
But what the source points out is that the stability we assume is entirely dependent on where we're sitting. It's a very physical thing.
Okay, so let's start there. Segment 1, the surprising 2 seconds. Let's establish the baseline first. Why are we so attached to 60 seconds?
Well, we're invested because it works perfectly here. Our whole system of timekeeping is just about dividing our planet's rotation our day into chunks we can manage.
So 24 hours in a day, 60 minutes in an hour.
And 60 seconds in a minute. It's called the sexagesimal system. We inherited it from the ancient Babylonians, and it just happens to divide Earth's rotational cycle really neatly.
So the number 60 isn't some magic number from the universe?
No, not at all. It's just a convenient tool for our planet's spin rate.
And that's the key. So what happens when we take that Earth-calibrated yardstick and try to measure Mars with it?
That's where you get the variance. The source material is really specific about this difference. It's small, but it's incredibly important.
Okay, give us the numbers. What's the precise difference?
A minute on Mars is functionally 2 seconds longer than an Earth's minute.
Wait, 2 whole seconds.
So if you ran, say, a 60-second experiment on Earth, and then you went to Mars to replicate it, your stopwatch would actually need to run for about 62 Earth seconds to complete what a Martian would call their minute.
That slight difference, that's the part that gets me. Most people hear time variance and they think of, special relativity.
Right, traveling near the speed of light or getting close to a black hole.
Exactly.
And that's why this is so compelling. This has nothing to do with relativity. It's purely mechanical.
It's just geometry and spin.
Precisely. It shows that these fundamental units we use aren't universal constants in the way we think. They're defined locally by the planet you happen to be standing on.
Okay, so that perfectly sets us up for segment 2. We have to get into the why. Why does time seem to stretch by those 2 seconds on Mars?
The core reason is just the difference in how long it takes to spin once, the rotational period.
Earth takes 24 hours, right?
Earth completes one rotation in 24 hours on the dot, or 86,400 seconds. Mars, on the other hand, it rotates a lot slower.
How much slower?
A Martian day, which they call a sol, takes 24 hours, 39 minutes, and 35 seconds.
Ah, so there it is. That extra, almost 40 minutes in a Martian day?
That's what forces the whole recalibration. You can't just take a longer day and use the exact same 60-second divisions and expect the units to mean the same thing.
You've hit the nail on the head. If the day itself is longer, but you want to keep the same number of minutes in it,
Which is what space missions generally try to do, just for scheduling convenience.
then those minutes have to stretch to fill the extra time.
They have to. There's no other way.
This is where we should get a little more technical, which is what our listeners want. The source material uses a specific term for this, right?
It does. It calls it the planetary time difference.
Planetary time difference. And the math behind it shows the 2 seconds thing is a bit of a simplification, isn't it?
Absolutely. It's a bit more nuanced. So let's just walk through it. On Earth, we have 24 hours. That's 1,440 minutes.
Okay.
You take our total seconds in a day, 86,400, and divide it by those 1,440 minutes. You get exactly 60 seconds per minute. That's our standard.
Right. Clean and simple. Now do it for Mars.
So the Martian sol, that one full rotation, is about 88,775 seconds long,
A bigger number.
a bigger number. Now, if we divide that by the same 440 minutes, because we want to keep that familiar 24-hour structure,
You get a minute, that is?
approximately 61.65 seconds long.
61.65 seconds. So there's the real number. Not quite 2 seconds, but 1.65.
Yeah, the source rounds it up to 2 just to make it more tangible for people, but that 1.65-second delta is the planetary time difference we're talking about.
And that fraction, that must be a nightmare for synchronization.
Oh, it's a huge challenge. It means Mars time is constantly drifting away from Earth time. Every single day, the Martian clock gains almost 40 minutes on the Earth clock.
So when the source material talks about time expanding or stretching, it's not a metaphor.
Not at all. It's a physical requirement driven by the planet's slower spin. The hours, the minutes, everything derived from that rotation gets re-indexed to be just a little bit longer.
And this is why Mars missions use a special time system.
Exactly. Scientists use something called Mars Time Coordinated, or MTC. It actually operates on a 61.65-second minute, just to keep the mission clock in sync with the local Martian day and night.
It's the ultimate localized definition of time. It makes you wonder why we even stick with the 60-second minute for space exploration at all. Why not just, I don't know, use a decimal system or base it purely on the soul?
That's a great question. And the answer is mostly inertia,
Habit.
habit, and human biology. We stick with the familiar 24-hour cycle because it aligns with our own schedules. It's easier for the team on Earth to coordinate if the Martian day still looks something like ours. It's a compromise.
So the minute itself is kind of a political construct as much as a physical one.
You could say that, yeah. It's defined by what's convenient for the planet's dominant species.
Okay, let's move into our final segment, the subjective experience. We get the math, we get the mechanics, but what does this actually feel like? If you were on Mars, would the minutes feel like they were dragging?
The source suggests the answer is yes, exactly. But probably not in a way that would bother you.
How so?
If you were born on Mars, or even if you just spent enough time there, your circadian rhythm would just gradually shift to match that 61.65-second minute.
So that subtle delay, it wouldn't register as lag, it would just be your normal pace of life.
Yeah.
The rhythm of the planet.
That's it. The environment on Mars just dictates a slightly slower rhythm and everything adjusts. The source uses this wonderful analogy to capture it.
What's that?
It says the day on Mars breathes more slowly than the day on Earth.
Wow. Breathes more slowly. That really puts a human, sort of an experiential feeling on that 1.65-second number, doesn't it?
It does. It captures that sense of a fundamental, inherent pace that defines a world.
And the implication here is huge for how we define time.
Yeah.
Like we said, it's not about high-velocity travel. The variability just depends on the simple rotational mechanics of where you're standing.
The planet itself is the clock setter. It means our minute, our most basic unit of scheduling. It's not some fixed universal number. It's a local agreement. It's tied to one specific planet's spin.
And for any kind of future interstellar travel or even just reliable communication between planets, this planetary time difference becomes, well, critical.
Absolutely critical. You can't just rely on the atomic definition of a second. You have to translate it into the context of the local planetary spin. Otherwise, you're always going to be 1.65 seconds out of sync every single minute.
That makes building any kind of multiplanetary infrastructure so much more complicated. It's not just making sure the clocks tick at the same rate.
No, it's making sure they're built to operate on fundamentally different rhythmic indexes. Every machine, every piece of software, it all has to be re-indexed for the soul. The moment you step off Earth, you leave the 60-second minute behind.
This whole deep dive has really recalibrated my own understanding. We start with this basic assumption, 60 seconds is constant, and we end up realizing it's just an Earth bias.
It's an Earth bias built on an arbitrary system. So let's quickly recap the key takeaways for you.
Yeah, let's do it.
First, the shocker, the variability of the minute. It's about 1.65 extra seconds on Mars, which we can round to 2 seconds to make it memorable.
And the mechanism behind it isn't some complex physics, it's just slower planetary rotation. Slower spin means the day is longer, so the minutes have to stretch. That's the planetary time difference.
Right. And we walk through the math, divide the 88,775 seconds in a Martian soul by the 440 minutes we like to use, and you get that 61.65-second minute.
And finally, that amazing analogy, the Martian day breathes more slowly. It just perfectly captures the subjective feeling of that rhythm.
So, we've shown that the humble minute is locally determined. It is not a universal constant.
And that leaves us with a final provocation for you to think about as you go about your day now armed with this knowledge.
If a basic measure of time, like the minute, is so unstable and just determined by the spin of our home planet, think about all the other constants we rely on.
Mm.
The metric system is based on Earth's circumference. We define weight using Earth's gravity. What other basic things in our daily life, things we never ever question, are actually just fundamentally localized and unstable when you look at them through a bigger cosmic lens?
How much of what we call universal truth is really just a highly specific terrestrial definition?